Hello there, Mr. Sutton here, bringing you the Algebra 2 11-2 lesson on analyzing arithmetic sequences and series. This will be another two-parter. In part 1, we're going to be writing rules for arithmetic sequences in a variety of situations. We'll do a little bit of that in part 2 as well. In part 2, we will also be tackling arithmetic series and finding sums of those. For our very first problem in this lesson, they're giving us two sequences, and they want us to determine whether each one is arithmetic with reasoning. Okay, well, what is an arithmetic sequence? This type of sequence is one in which the terms have what is called a common difference, which we refer to as the d value of these. So an example of an arithmetic sequence would be one we've actually seen before, 2, 4, 6, 8. This is an arithmetic sequence because if you find the difference between any two pairs of terms, like 4 minus 2 or 6 minus 4, 8 minus 6, it's always the same number. You're always adding the same number to get the next term. Now, if we were to graph this out, and I'll just do this on Desmos real quick. So let me pull up a table, and let's just do the first four terms. It'll be pretty clear after those. So we have n values of 1, 2, 3, and 4. And now my terms themselves, 2, 4, 6, and 8. And if we look at the graph of this thing, if we were to connect the dots, we can see that this thing is pretty clearly a linear sort of pattern. So I'm going to say an arithmetic sequence follows a linear pattern. I don't want to say it's a linear function because that would imply that there was something in between these points here, and there isn't, right? It's only the whole numbers that we're plugging in for our domain, but it's a linear pattern. For that reason, a lot of the things that we use when dealing with lines also kind of work with arithmetic sequences. For example, when we talk about lines, we talk about a slope. Well, the slope of this line, if we were to come up with the slope, we'd be going up 2 over 1, up 2 over 1. So this would be an m value of 2. It turns out that the m and the d really are kind of the same thing. You can think of the d as the slope of an arithmetic sequence, but I do put slope in quotations because, again, this is not a continuous function. So with all this in mind, we're going to try to figure out whether these sequences are arithmetic or not. And really it all comes down to whether or not they have this common difference. So with that in mind, pause the video and see if you can use that to get to the bottom of this mystery. All right, let's deal with part A first. So finding the common difference. So let's just subtract each pair of terms and see if we keep getting the same number. So negative 2 minus negative 9, that's a little tricky, but that's negative 2 plus 9. So that's a difference of 7. Then 5 minus negative 2 or plus 2 is also 7. 12 minus 5 is 7. 19 minus 12 is 7, and this keeps going, but based on what we've seen, it seems that this is an arithmetic sequence because there is a common difference that we're noticing here. All right, well, let's check out the next one. So for part B, 15 minus 23, that's going to be negative 8. And how about 9 minus 15? Well, that's negative 6. We could keep going, but already we see that there's not a common difference. So this is not an arithmetic sequence, no common difference. For this problem, they're asking us to write a rule for the nth term of this sequence and then find the 20th term. So we're going to talk first about how to find the nth term of an arithmetic sequence, and then if this happens to be arithmetic, we can use that here. So recall that an arithmetic sequence follows a linear pattern. For that reason, a lot of the tools we used for lines can be applied here as well. Recall that the point-slope form of a line was y minus y1 equals m times x minus x1, where x1 and y1 were basically was an x and a y value of a point that you knew, and m was your slope. So if you wanted to rearrange this to solve for y, you could rewrite this as y equals y1 plus m times x minus x1. And what this little formula allows you to do is take a point that you already know, x1 and y1, plus the slope, and then if you plug in the x value of another point, it'll give you the y value of that point back. That's kind of what we're asking for here. we've already got a few terms. This is actually kind of like having 4 different points, and we're trying to find out term number 20. That's like having an x value of 20, and y would kind of be your a sub 20 in this situation. So what we can do is kind of reframe this in terms that we can think of an arithmetic sequence in. So this will be the nth term of an arithmetic sequence formula here. So we're going to call, instead of calling this y, we're going to call this a sub n. So this is the term that you want in the sequence. y1, that's the output of some term that you know. So we could actually use any term that we know, but we usually use typically the first term, so we're going to use a1 there, although you don't have to. For the m value, well, we said that the slope, quote unquote, of an arithmetic sequence was the difference, the common difference, so we're going to write d instead of m there. For the x value, that's the input you plug into the sequence to get the term back. So that's the n that you're plugging in for your nth term. And then if we're subtracting x1, that's the x value of the term that you know. If you're using the first term, then your input was just 1. So we're going to do minus 1 here. So this is kind of a specialized, kind of specific form of the nth term arithmetic sequence. It's the one we use most of the time. If you really had to, you could use, for example, the third term, a3, and use a 3 here instead of a 1. So these ones go together. Whatever number this is, this one has to be as well. But we usually use the first term. With all that in mind, how can we apply that to this situation? Well, we can't apply it at all unless this is an arithmetic sequence. So take a moment to determine whether this sequence is arithmetic or not. All right, so hopefully you've kind of figured that out for yourself. If we take the difference between any two of these terms, like 8 minus 3, 13 minus 8, we see that we do keep getting the same number. So this is an arithmetic sequence. So if that's the case, in order to use this formula and get an nth term formula for this particular sequence, we need to figure out the a1 and the d values. And then we need to plug those in. The n is going to stick around and the a sub n is going to stick around until you need to actually plug something into it. So with that in mind, I'm going to have you try to find the nth term formula for this sequence, and then just for fun, plug 20 into that to get the 20th term. All right, let's see how that worked out for you. So I'm just going to rewrite my nth term formula again. And a1, that's the first term, so that's 3. That's pretty easy to find. The d value, again, we're just taking one of these terms and subtracting the one before it. So 8 minus 3 works, so does 13 minus 8. Any of these will work. So that's going to be a common difference of 5. So plugging that in, we could say a sub n equals 3 plus 5 times n minus 1. And you might need to simplify this in order to match it with, one of your answer choices or whatever you're using it for. So if we distribute this 5, we end up with 5n minus 5. And then if we combine the 3 and the negative 5, we can write 5n minus 2 for our final simplified a sub n formula. Now, if we do want to actually use this to find the 20th term, then we would just be plugging 20 in for this n value. So 5 times 20 would be 100, minus 2 would give us 98. Now, just a quick sort of follow-up to this, why do we care? How does this help us out in a real-life situation? Well, it turns out there's a lot of real-life situations that we called linear, but a linear function doesn't actually model them the way they work in real life. For example, think about the money you have after working for a certain amount of time at a job. So let's say that you, for your first hour at the job, you get $3, and then for every subsequent hour, they're paying you $5 an hour. Now, the trouble with using a true linear function on that is that they're not going to pay you for, 2.25 hours or something weird like that. They only pay you for every discrete hour of time that you work. So if you want to find the money you have after 20 hours, a linear sequence is going to work a little bit better than a true linear function. Here's another example for us to try out. They still want the nth term and the 20th term. This time around, though, they've given us the sequence in graph form instead of just giving us a list of numbers. So pause the video and give this one a shot. All right, so did you check first to make sure this was an arithmetic sequence? We always want to do that if we're going to use that arithmetic formula. So just taking a look here, just graphing it out and connecting the dots, we can see that it's a linear sort of pattern. And if we look at the differences, 10 minus 15, 5 minus 10, it definitely is a common difference. So yes, this is arithmetic, and we can use our arithmetic formula, a1, again, plus d times n minus 1. So this time around for our d value, we can do 10 minus 15 or any of these other subtractions. So that's negative 5 for the d value. a1 in this case would be this first point, so it would be the 15 piece of this, the output. So we've got 15 minus 5 times n minus 1. And then let's distribute that negative 5. So that's going to be 15 minus 5n plus 5. And then finally combining the 15 and the negative, or the positive 5, we end up with negative 5n plus 20. And then finding the 20th term, we've got negative 5 times 20 plus 20. That's negative 100 plus 20, which is going to give us negative 80. For this next problem, they are no longer concerned about the 20th term, but they still want a rule for the nth term of this arithmetic sequence. So how is this different than the last few problems? Well, they didn't give us a whole list of numbers. They actually just gave us a single term, the 19th term, which apparently is negative 45, and they actually just told us the common difference. So in some ways, it seems like they're making this a little bit easier for us. So we're like, okay, they even actually said it's an arithmetic sequence, so let's write out our arithmetic formula. A sub n equals a1 plus d times n minus 1. And let's go to town and plug stuff in. Well, d we already know. However, a1, they gave us a19. They didn't give us a1. They didn't give us a list, so we don't know the first term. That means that we're going to want to go back and solve for that first term. So the good news is, even though we don't know a1, we do know a specific a sub n and n. They gave us a sub 19, and 19 is the n value for that. So you can actually plug in for the a sub n and the n and use that to help solve for this a1 if you need to. So with that little hint in mind, pause the video and see if you can make that magic happen to come up with an nth term formula for this thing. Alright, so let's plug a bunch of stuff in. So for a sub n, again, we're going to use negative 45. a1, we don't know that yet. d, we know, was negative 3. And then the n value is going to be the 19 that we have to plug into whatever this is going to be to get the negative 45. So 19 minus 1 in there. So let's go ahead now and simplify this a little bit to solve for a1. 19 minus 1, that would be 18, times negative 3 is negative 54. And if I add that to the other side, I see that a1 is going to equal 9. So plugging that back in with my d value now to this original formula, we can write a sub n equals 9 minus 3 times n minus 1. And then just like we did before, let's simplify this. So that's negative 3n plus 3. And then combining the 9 and the 3, we can write negative 3n plus 12. So with that, we are concluding part 1 of this lesson on arithmetic sequences and series. Pause the video and try out some problems where you're getting these nth terms, and then we'll use what you've learned in part 2 to do a little bit more work on nth terms of sequences, and we'll also take a look at series. See you then. Welcome back for part 2 of our lesson on arithmetic sequences and series. So for our opening problem on this one, they've gotten even sneakier than the last example. The last example, you might recall, they didn't tell us a1, so we needed to plug in a specific term in order to find it. Here, they also did not tell us the common difference, whereas they did on the last example. So that's kind of the big new thing on this one, is we have these terms, A7 and A26 in this case that are not even consecutive terms. They're not right next to each other. So I can't just do, for example, 93 minus 17. That would not give me the common difference. That would give me the difference between, a whole bunch of terms, not just two of them. So how could I figure out that common difference with these non-consecutive terms? And this goes back to the fact that these arithmetic sequences follow a linear pattern. So one of the tools we use with lines is if I have 2 points, I can find the slope, which we said was basically our common difference. We can find the slope if we use the slope formula. If you remember the slope formula, that was y2 minus y1 over x2 minus x1. Applying that to this kind of a situation, we can do a arithmetic sequence version of that, where our common difference, or our slope here, is basically subtract the two terms and then subtract the indices of the two terms. So you've got output 1 minus output 2 over input 1 minus input 2. And this is how we could figure out the common difference in a situation like this. So with that in mind, pause the video and see if you can use that to take this one the rest of the way. Alright, so let's find that common difference. In this case, this is going to be 93 minus 17 over 26 minus 7. So outputs minus output, input minus input. And then 93 minus 17, what is that? 76. And we're dividing that by 19. So I believe that's going to come out to 4 when all is said and done. But you could check it on a calculator if you wanted. So that gives us our common difference. Now remember, we don't know what A1 is. So when I write out this formula here and I go to plug in D, I'm realizing, hey, I still need this A1. So that means I also, just like I did on the last example, need to plug in one of these two terms in order to figure out the A1. Now it doesn't matter whether you plug in A7 or A26, just pick one and be consistent. I'm going to go with 7 and 17 because those numbers are smaller. So I'm going to do 17 for my A sub n. My A1 I'm still looking for. My D is going to be 4. And because I picked 17, I have to go with 7 because that was the index that gave me 17. So I'll do 7 minus 1 here. And then 7 minus 1 is 6, times 4 is 24. 17 minus 24 gives us negative 7, so that's my A1 value. Plugging that back in now, we've got negative 7 plus the common difference 4 times n minus 1. And then doing that little simplifying dance at the end, we've got negative 7 plus 4n minus 4. And then combining our constants, we end up with 4n minus 11. For this next problem, they're asking us to find the sum of 3i plus 7 from I equals 1 to I equals 20. So we know that there's a few ways we could already try to do this. One would be to plug in the integers 1 through 20 into this expression here and add those 20 different items together. That would be kind of long and tedious and wouldn't work well if this were like a 200 or 2000, so it's nice if there's a better way to do it. We also saw that we could split this up into two different sums and take out a 3 and take out a 7 and use some special formulas for the summation of I and the summation of 1. And that's another way to do it, but that's also kind of clunky and a little bit drawn out. So this is essentially an arithmetic series. We know it's an arithmetic series because this is a linear sort of formula, linear pattern. So that means it's going to be an arithmetic when you actually write out these terms. It'd be nice if there was a shortcut for finding the sum of an arithmetic series. It turns out there is. So here I'm going to give you the formula and then I'm going to kind of explain the intuition behind it. We're not really going to prove it, but I'll show you kind of why it works. So our formula is we're going to have n, the number of terms, times a1 plus an, that's the first term plus the last term, all of that divided by 2. Now, why does this actually give us the sum of one of these series? So the intuition behind this, when you're adding a1 and an and dividing by 2, you're essentially finding the average value of a term. You've got the average between the first and the last term. but because of the kind of the symmetrical way that these arithmetic series are set up, that, it turns out, is the average of the entire series. And if you take the average value of the whole series and multiply it by the total number of terms in the series, well, you get kind of what the whole series adds up to. So we're going to use this formula in this situation. There are still kind of a few kind of details to iron out, though. And we could probably figure out based off of what we know about the number of terms in one of these series. But how about a1 and a sub n? Because that's not directly spelled out here. So you can actually find a1 and an, both of those, by just taking your lower limit and upper limit of summation and just plugging those into your summand to find those. So that would be a quick way to get your first and last term for something in this format. So with that in mind, pause the video and give this formula a test drive. All right, so let's come up with our three different things that we need to use this formula. Our n value is going to be 20. There's 20 terms in this series because we're starting at term number 1, and 20 is the last term number. So 20 terms. If you didn't start at 1, though, be careful. You can't just assume that your upper limit is your n value if your lower limit is not 1. Now, how about the first term? That's going to be 3 times 1 plus 7. So that's going to be 10. And then to get the nth term, the 20th term in this case, that's going to be 3 times 20 plus 7. So 60 plus 7, or 67. So plugging these three things into our formula, we're going to end up with 20 times, we've got 10 plus 67, all of that over 2. And I wrote Sn, or S20 here. That's the sum of the first 20 items. We could use a calculator. We probably don't need one, though. So 10 plus 67 is 77. And I could reduce the 20 and the 2 to just have a 10 up here. 10 times 77 would give us 770. So there we are. So for our final boss battle, you might want to channel your inner Kevin Spacey, because we're going to be making a house of cards, similar to the one shown here. Not a real house of cards, just a theoretical one, but you get the idea. So this is a two-part problem here. The first part, they want us to write a rule for the number of cards in the nth row when the row 1 is shown up here in the diagram. And then based on that, we want to know how many cards we're going to need to make a house of cards with 12 rows. I mean, this is good to know before you start building the house, right? Make sure you have enough cards for the whole thing, because you can't really leave these for too long and expect them to stay standing. So pause the video and first see if you can figure out the number of cards in the nth row. All right, so let's take it row by row and see if we can come up with a pattern. So for row number 1, we can very easily count that. 1, 2, 3. There we go. For row number 2, we could probably count that as well, but let's try to think a little more abstractly. You see, each of these rows is built by putting a bunch of triangles on top of the row underneath it. So and each of these triangles, well, clearly has 3 cards that make it up. So in row 2, we've got 2 of these triangles. So 3 cards per triangle times 2 triangles is giving us a total of 6 cards. And then in row 3, kind of the same pattern. Now we've got, again, 3 cards per triangle times 3 triangles gives us 9 cards. And then row 4 would have 12, and then we'd have 15, and so on and so forth. So in general, then, following this pattern, 3 times 1, 3 times 2, 3 times 3, our nth row is going to have 3n cards in it. So with that in mind as our formula for the nth term of this, it is an arithmetic sequence, right? Because you keep adding the same number each time. See if you can figure out the number of rows, or the number of cards you're going to need for a total of 12 rows. So this is more of a series now, adding all these different rows together. Give it a shot. All right, so again, it's arithmetic, so we're going to use our arithmetic sum formula, n times a1 plus an over 2. So let's get the n, a1, and an for this. The number of rows is our n value, so that's going to be 12. For a sub 1, that was the number of cards in the first row. We discovered that very quickly. That was 3. For the nth row, the 12th row, we just need to use this formula here, 3 times 12, which means we have 36 cards in that 12th row. So putting all this together, we have a bunch of stuff divided by 2. Specifically, we've got 12 times 3 plus 36, all of that over 2. And could we do this without a calculator? Yeah, we might be able to. But just to be on the safe side, let me plug it in Desmos. So let me make a fraction here. We've got 12 times 3 plus 36. All of that divided by 2 gives us 234 cards to make a 12-row house of cards. I don't think I've ever seen one make a house that big, but hey, it could happen. So while our house of cards is still standing, this seems like a good time to walk away from it. Until next time, Mr. Sutton signing off.